Hassanizadeh.
Just the first name?
Majid.
Majid.
Okay, we're up here practicing the introduction. All right, this is our final talk.
Yes.
Okay, so our last talk is by Majid Hassanizadeh. There, pretty good.
Very good.
Okay,
Good.
take it away.
Yeah, good afternoon. It's a great pleasure to be here, and thank you to Richard, John, and David, and others who organized this. So I'll talk about two-phase flow, but this is actually three phases, because this is two-phase flow through a porous medium. And although this could be a deformable porous medium, but the formation is very small. So the interest is not, so the formation of porous medium is not very exciting. And it's mainly the flow of the two fluids that's exciting, especially when it comes to production of oil and gas. Now then it really becomes exciting and important.
Not anymore.
Not anymore, that's right. Yeah. Shale gas, maybe. So I would like to acknowledge the collaborators. These are the first four are the PhD students in the past. Now they are at different places, and colleagues from other universities. Yeah, I'm interested in two-phase flow in porous media. I'm sure many of you know applications of two-phase flow in oil and gas reservoirs, environmental pollution problems where organic liquids seep into the soil and groundwater. But there are a number of other very interesting applications of two-phase flow that I'm myself gotten interested in, and I have projects. For example, penetration of ink into paper. That's also a, let's see whether this works. I need to have my, yeah, doesn't work. Yeah. So you see that when you put in an inkjet printer, when the ink is put on, arrives on the paper surface, then starts to penetrate in. These are images from a confocal laser microscope, where under a microscope we can see ink going into the into the fibers of the paper, and we are trying to understand that, and actually more or less the same mechanisms as in other two-phase flow problem. This is another application. Many of you recognize it, sounds like it. And so this is the penetration of liquids into a diaper. One liquid. And the diaper is really a complex piece of technology. There are four layers. In the core layer, then you have what is called superabsorbent polymer that absorb anywhere from 30 to 300 times its own volume. Can absorb, and so then again there is first imbibition takes place, and then drainage takes place. So it's very similar unsaturated flow processes, and then fuel cells are, as I said, projects I'm currently working on. In a fuel cell, we also have now fuel cell. This is a hydrogen fuel cell where hydrogen and oxygen are they let them to react and produce energy, but the energy is harvested as electrical energy, and that results in water being produced. So in the system we have water, and we have, oh, I didn't have, I had another image. It doesn't come. Now there is an image of water droplets formed within the fuel cell. So that's another two-phase flow system. We studied these, among other ways, using micromodels. So micromodel is what they call microfluidic device. You see an image of it here. These are thousands of pores. They have made in a transparent slab. The slab is made of PDMS, and then we put another slab of PDMS on it, and we can seal it. And then we put these reservoirs on the two sides, so we can inject liquids into this or fluids, and then we can look into this under microscope or using cameras. So as I said, there are thousands of pores in here. There are bigger pores and smaller pores. The average sizes could be 40, 50, 60, and 70. We make different devices, and the depth is usually the same as the average, the mean pore size. In this particular micromodel, which is made of PDMS, PDMS is a hydrophobic material, so water dyed with ink is the non-wetting phase because it's hydrophobic, and another liquid we use, fluor inert, is the wetting phase. I don't know whether you're familiar with wetting and non-wetting terminology. A solid has, when it is in contact with two fluids or more fluids, it has a preference for one of these fluids. It would love to have that particular fluid next to it, the solid surface being covered by that, and it doesn't like the other fluid. So the one that it likes, that's the wetting phase. The one that it doesn't like is the non-wetting phase. So if you take a sugar cube, bring it in contact with the tea, you know that tea rushes into that sugar cube. And you cannot put the water out of the sugar cube that easily anymore. It won't happen by itself, whereas water rushes in by itself. And the reason is that the surface energy of sugar crystals and water is much smaller than the surface energy or interfacial energy of air and sugar crystals. And therefore, as all systems tend to go to a lower energy state, the water rushes in there and then replaces the solid air surface with water solid surface. So there is always one phase that is wetting phase, the other phase is the non-wetting phase. There is, unless there are some cases that doesn't matter, then usually those are miscible liquids or fluids. Okay, then this is like a PDMS, and then if you look, we put that PDMS, say here under a light goes through it, between these two, these are reservoirs, we can inject one or the other liquid in there, light goes through it, goes horizontally through this lens. In this box, we make from one image 4 images in the 4 perpendicular directions. So in this direction, the other, here and here. And there are cameras receiving these images. And we need to do this because, you know, these are long models. I didn't say that. This is about, let's see, I need my, so this is about 35 millimeter, 35, and this thickness is about, the width is about 5 millimeter, okay? So, and if you want to see this with a microscope, you can see only part of it. So we have created this system where with the 4 cameras, one of them gets this part of the image, the other gets this part, the other this part, this part. So we can at any given time see exactly what happens throughout the whole system dynamically and all parts of it. And then we get images like this. This is an image from one of the cameras. What you see here, the triangles are the solid phase. The pore between them, as I said, there are really thousands of pores in here. They are filled with the wetting phase, in this case fluor inert. And then from this side, we inject the non-wetting phase, which you will see it in dark color in black. And then if I get my, then you should be able to see, or not, it's not coming, yeah. See, there is the, you see that the liquid rushes in there and moves into it. Now then, at some point, we can reverse the process. This is called drainage. The wetting phase is displaced by the non-wetting phase, called drainage. And then when we put the wetting phase back in, that's called imbibition. It's imbibed into it. And what you see here is that the movement of the black phase, the dark color, will not occur if these interfaces between the two liquids don't move. If the interface is stuck because of capillary forces, because the interface cannot go into small pores. As I said, this solid has preference for the wetting phase. And the smaller the pore is, it's more difficult for the non-wetting phase to go into that pore because it has relatively more solid area compared to the volume of the pore. So it's more difficult for it. The capillary force is larger than it cannot go in there unless you increase the forces. So the interesting thing is that these interfaces play a significant role in whether this process would occur or not. And you can see more of it. This is another one where we have discontinuous phases. Oops. I don't know why this is playing games with. Okay. So you see these are, the black is again the non-wetting phase, and now we are injecting the white, which is the wetting phase, at large velocities, and this causes what we call mobilization of these trapped phases. Can you see them? See, they're moving here. And the other ones that they don't move is because the interface is stuck, actually. I'm making this, I'm emphasizing this, because in these two-phase flow problems, the fluid-fluid interface playing a major role in letting the process happen or not. Also, as I said, the solid-fluid interface is very important for this process to occur because of those energetic effects there. So in fact, as I said, you will have, so let me get my...
For the movies that you just showed,
yeah.
Did you say what the frame rate was? Or I presume the part of the direction motion is just that you have a low frame rate? Or is that...
No, this is especially no, it is, that's the way it happens, that the frame rate is about 32 frames per second. And you probably, some of you have heard of Haynes jumps. These are Haynes jumps, that the interfaces will not enter a pore until the pressure builds up, and then it can move. And once it moves through a pore, it usually goes all the way until it comes across a yet smaller pore, and then it cannot move. Pressure has to build up, and then it goes through. So these are real jumps that occur.
Can you explain why the jumps were quite so regular in time on the second movie?
They are not, are they? Let's see. No, they also build up, definitely. There's something wrong with my pen here. Yeah, see? They're not regular. They jump. And this also, you see, they are all, this is real time. So, yeah?
I was just wondering, what's the viscosity ratio between the two fluids?
For these two particular ones, the fluorinet is slightly more viscous, about 20%.
Small difference if you have a capillary thing.
It's not a huge difference, no. No. Actually, that fluorinet, you can get it at different densities, viscosities. We especially got one that's not very different. Okay. Now, as I said, the reason that the interface, the wetting phase goes in is that the, let's see, do I have my... If I show the interfacial tension between, or the interfacial energy between the solid phase, I can't write this, between solid phase and one of the fluids we call non-wetting phase. There's something wrong with my pen. I dropped it and I think it's now not working.
It's a blackboard. Blackboard.
Yeah, maybe I use a blackboard. That's a good idea.
Good technology.
Yeah, it's not always helping. So the gamma solid and then with the non-wetting phase, can you read that? Here. Gamma is the interfacial energy or per area or interfacial tension between solid and the non-wetting phase. This is usually larger than, it must be, between the solid and wetting phase. And the difference between them times the area between solid and any of the fluids, for example, solid and non-wetting phase, that's the energy that's being released. And in order to show that this really happens, I believe I have, oh yeah, because I'll come back to that in a minute. So two-phase flow is a major problem, major process, and the equation, it's actually a complex process, but the equations that are currently being used for modeling it are very empirical in nature. They cannot they have not been mostly developed by doing a rigorous derivation of equations, definitely not in the early times. And take Darcy's law. I mean, we also saw Darcy's law being used today for the movement of melt and the mantle itself. Now, Darcy equation was developed by experiments he did on a simple system. This is sand. It was homogeneous. It was non-deformable sand, isotropic, and then he put this water difference in hydraulic head between the two sides, and he measured the flow rate, and it was linear. So it was from such a simple system, it's now being applied to whatever system you can even think of. And you would say, yeah, well, I mean, Darcy's law was, therefore, for one steady state flow of almost pure incompressible water in saturated, homogeneous, isotropic, rigid, sandy soil under isothermal conditions. And this is the equation if you write it in terms of hydraulic head. It's a linear relationship. And now it's been said, and the hydraulic head is defined as pressure head plus elevation head, and now it's assumed to apply to 3D unsteady state flow of two or more compressible fluids with any amount of dissolved matter in heterogeneous, anisotropic, highly deformable porous media under non-isothermal conditions. See how many more processes are added. And of course, then Darcy's law that's applying to this system must be much more complex than the other Darcy's law, right? Wrong. It's exactly the same. There are some indices added, but the driving forces, the relationship is exactly the same. The head is also defined in the same manner. And you say, well, okay, how was this extension done? Now, I apologize if somebody is here that has seen this slide because I've shown it other places, but it's my favorite slide. So here's how you do extension. You say, okay, Darcy's law was for a finite system. If you want to make it in a differential, one-dimensional, you replace del H with minus dH dx. Now you've got Darcy's law for a one-dimensional. If you want to make it the unsteady state, all you need to do is say H is a function of not only x but also time. So you replace the total derivative with a partial derivative. And if it is three-dimensional, now we write it once in each direction. There you go, three-dimensional. And if it is anisotropic, then replace k by kij. That's all you need to do. It's now anisotropic. Heterogeneous, don't do anything with the Darcy's. You could just assume k is a function of space. No. And if it is deformable, well, then we assume k is a function of porosity. And if it is unsaturated, so there is water and air, and the water is moving, air pressure, it doesn't change much, well, then again we write the same equation, but now we assume Kij to be different from the saturated permeability. We call it hydraulic conductivity. It's a function of water content. And if it is two-phase flow, now, there again, we write Darcy's law once for water, or the wetting phase, and once for the oil, or the non-wetting phase. And all you need to assume is that this K now is a function of saturation. So we usually say there's a relative permeability. This is this one here. This is the relative permeability. This is saturated permeability. And therefore, the relative permeability must be less than 1. And for both the oil and the water, or the wetting phase and non-wetting phase. Then should we extend this to three-phase flow? That is 4 phases, 3 liquids. How do we extend that? We write it 3 times. 4-phase flow, 4 times. It's true. But you see, of course, so what happens to those interfaces and interfacial energy, and that there is such a complex behavior of the interfaces? It's not in here. This is promising that the only state variables are saturation and pressure. I show the equation in a minute. So to me, this is not much of an extension. To me, this is adding bells and whistles to a simple equation. Now it looks more complex, therefore it's valid, must be valid for a more complex system. And I would say you have to go the other way around. You have to have a complex system equation for a complex system, and then make assumptions to simplify it for a simple system. And there are people who say, yeah, but that it works. The equation works. Why should we worry about it? And the truth is, it doesn't work. And that's what I'm going to show. So these are the equations. You have seen this. This is the mass balance if the mass density is constant for each phase. So you write this twice for each fluid phase. So you write this for the oil or water, or as I say, wetting phase and the non-wetting phase. So you've got two equations here. This one also, Darcy's law in pressure form. If you substitute there, you get two equations, but you have got three unknowns because there is saturation unknown for one of the phases. The sum of saturation is 1. So SW is unknown, and then the pressure of the wetting phase and the pressure of the non-wetting phase, they are unknown. Okay, so there are three unknowns and only two equations. So what do? We introduce another equation, and that's saying that the three unknowns are related to each other. The difference in the pressures of the two phases is a function of saturation. Now, some of you may know this is called capillary pressure. And they call it capillary pressure, but actually it doesn't matter whether it's capillary pressure or not, because we just are interested in that first equation. So you can simply forget that it's called capillary pressure. And that's the way also they measure it. They measure that pressure difference. Because capillary pressure, indeed, at the scale of one meniscus, is the difference between pressure of the two phases. But this is not one meniscus. These are macro scale equations, averaged over thousands of pores and thousands of menisci. So you cannot say, oh, that is the case, because this is now not at one meniscus location. Okay, so it doesn't matter what it is. And then what, as I said, this relative permeability is also assumed to be a function of saturation. Now, this looks okay then. We have three equations because there are two from here and one from here. So there are three equations, three unknowns. We are all set. But these equations are promising that an algebraic relationship between these two and between here exists. And uniquely algebraic relationship. And the truth is it doesn't exist. And I show you that. And as I said, they promise that the only state variables you need to know is saturation and two pressures. You know them, then you know everything, which is not true. Because as you know, at the micro scale I showed you, you need to know something about the interfaces, the menisci. Where are they? Otherwise, nothing will happen. So the capillary pressure, the first one here, as I said, this equation is usually has a shape like this, where this is the pressure differences and this is saturation. This is some of the curves you see in the textbooks, and these are data points. I'll go back to this. The relative permeability curves are like this. This is for the wetting phase, because this is saturation of the wetting phase from 0 to 1. And this is for the non-wetting phase, or the oil. But when people do experiments and measurements and determine these curves, they find that it's not only just a function of saturation, they are also a function of pressure gradient or flow velocity. Now that's confusing, because I was supposed to have a linear relationship between flow rate and pressure gradient, and the proportionality constant or coefficient is relative permeability, but I find that relative permeability is a function of pressure gradient, so it's not linear. Now, then what should be the correct relationship? Maybe one has to investigate that. Moreover, when they do measurements, as I said, rel perm must be less than 1. They find rel perm values up to 14, which just doesn't make sense. That means when two fluids are present, one of them moves faster than if it was alone. That cannot be. Yeah?
Couldn't a low viscosity wetting fluid lubricate a non-wetting phase that's very viscous? I thought that was the standard explanation.
It could, but not 14 times. And also, it would be the case if the wetting phase is present at very small saturations. But you see those values at saturation of 50, 40% of water. So even higher here. Doesn't...
But possibly a silly question. What are the error bars like on those points? How certain are they?
I don't know. This is from a publication by Stefan Berg, who is from Shell Research Lab in Leipzig. But definitely, once again, it's nothing compared to at 14 times. Yeah.
But, 14 doesn't seem like a very big contrast in permeability. I mean, we have
No, this is relative permeability. So relative permeability, as I said, they write the permeability to a given phase, so for example to the non-wetting phase, is less than the saturated permeability. Or if that phase was alone, you measure a permeability. Now that it's not alone, it must be less. Do you agree to that?
Back to the other question you got about if one of the phases is much lower viscosity, why do you think that 14 is such a big number?
Yeah, but if the pores are filled not by single phase, by some other phase, permeability must be less. It's not a matter of, it can be that, because now you have a smaller area to move through.
You have a different boundary condition.
No, but this is an intrinsic property of the medium. It's not depending on the boundary condition will tell you the pressure gradient could be larger. But the permeability itself, the coefficient that relates permeability velocity for the same pressure gradient, if you have pores completely filled by fluid 1, you will have a bigger flow rate if it is partially filled by another fluid. This is the constant of real perm. So this is saturated permeability is K, and this is some coefficient times that. It should be less than 1. I can come back to this later on, but this is by design, K relative permeability is supposed to be less than 1. About the capillary pressure saturation curve. So I said that they say Pm minus Pw must be a function of saturation. The way these capillary pressure curves are measured are that you take a sample of soil, put it between two reservoirs. This could be air, could be oil, could be the non-wetting phase. And here is water. And if this is saturated with the wetting phase, like a sugar cube filled with the tea, now you can close this around it, and the air will not go in there. The sugar cube will not let or sand will not let the water go. Air will not go by itself. You have to increase that pressure before it can go in there and displace the wetting phase. So if you plot pressure difference between these two reservoirs as a function of saturation, when saturation is 1, nothing happens. You increase that pressure a little bit, and still nothing happens. At some point, this is called entry pressure, that air goes in there, displaces the water. Now, then they wait until no movement occurs anymore, because this is the way it's measured. It's quasi-static measurements. So then when nothing moves for that pressure difference, this is the pressure difference here, for this pressure difference, and then there is a small change in saturation, they give a data point. Now increase that pressure again, and now more air goes in there or the non-wetting phase, water goes out, and that gives you another point. Each time they have to wait until nothing happens. So then they get a full curve, and this can take up to a week to get this curve for a soil sample, for example. Now you put the curve through it. This is called drainage curve or drying curve. Now you can reverse the process, reduce that pressure, let the water go back in. Now, it would have been great if it goes back along that line. It doesn't. It goes along a different line. It's called the wetting curve or the imbibition curve. And if you were going to reverse this process halfway, don't go all the way, reverse it here or reverse it here, you get yet different curves. These are the scanning curves. In imbibition, you get the scanning curves in drainage. So it's not a unique relationship anymore. And it is as I said, it takes a week. If you want to get all of this, it will take you a month. And then they use these kind of curves to model a process like the penetration of urine into diaper, which is really fast process. It happens within seconds. And they use a curve for diaper. For a layer of diaper, it takes 12 hours to get one of these curves. And then they use it for a process that takes seconds. So something isn't coming together there. So that's been said here. So you can ask the question, so how about if, like in a diaper or in a paper, we increase this pressure not infinitesimally, but increase it to a large value such that with that, for that large pressure difference, all the water can go out, will go out, and will be displayed. How would the curve look like then? Would it be the same as this, or will it be a different curve? Now, to do that, you need to measure the pressure of each phase inside the sample, and we have had a system. I'll show you in a minute. These are real scanning curves. For drainage scanning curve, imbibition scanning curve. And I think what is really happening here is that there exists no curve. These are equilibrium points. You actually have an equilibrium region. Every point here is a potential data point relating pressure difference to saturation. So it tells you actually the saturation is not the only state variable. You need something else to provide this relationship. I'll come back to that. You can also see that here. These are from our own micromodel experiment. In this image, we have a saturation of black, 24%. But the pressure difference between the two fluids is 4,000 Pascal. Then we do imbibition and drainage. We come back. This is the same saturation, 24%. But now it's distributed differently. So you need to macro scale measure of telling the difference between these two, and saturation is not enough. You need something else. And this tells you something else has to do with these menisci behavior. So that's why you see here interfacial area between the wetting phase and non-wetting phase. This is the area of these interfaces. Is here 18, here is 30. It's a big difference. Okay, so this actually suggests that interfacial area between the fluids is another potentially state variable. Yeah?
When you measured the area between the wetting and non-wetting, are you assuming that the pores, throats are completely filled? So it's only at the ends? The pore throat are not necessarily filled. It depends on the shape of the pore throat. If the pore throat is tapered like that, now then the interface coming and again gets stuck somewhere in between. You have a lot of contact with the solid.
I think the question is getting at, do you have any draining films on the pore walls, for example?
Oh, I see. Yeah. No, we don't have that here. But even if you have it, still you will have a different distribution. When you do drainage and then you do imbibition, you come back, you get totally different distribution, even if you have that. So it tells you for the same saturation, you need something else to tell you this difference in the distribution. So as I said, the reason that water invades a hydrophilic material because the system goes to a lower energy state. That surface energy of air-solid interface is much larger than that of water-solid interface. And at the imbibition, that energy is released and the system goes to a lower energy state. And you can ask yourself, what does happen to that energy actually? And I'm going to show you, this is a video from a very recent experiment we did. This is a piece of paper. And then we inject water into this piece of paper and then measure the temperature as the waterfront moves in here. And we do this measurement of temperature in two ways. One is using a thermometer, the other using infrared camera. And I'll show you both of them. So this is, I need to get my, so you see on the right, water is being added to the piece of paper. We put the paper between two plastic tape. And then here is the thermometer, and we're measuring the temperature. The paper, the water, thermometer, they are at the same temperature. And then we see that as the water approaches this thermometer, temperature goes up. And it goes up is like 2 degrees. This is a paper of only 1/10 of a millimeter. And this is, oops. Let's try that again. Yeah. So you see water comes in, and the temperature as its water moves, you see that here. As the wetting front approaches the thermometer, temperature goes up. And once the wetting front passes, temperature goes back down to what it was. So this is energy release, simply becomes solid air interface is replaced by water air solid interface. And you'll see that here with a infrared camera. See, water is coming in, and temperature everywhere is the same, except at the front, the temperature goes up. And it's an irreversible process, because now if you reverse it, you put the water goes out. I don't have that one here. You see the temperature doesn't change. Drainage doesn't change. You actually, it's only imbibition that releases energy. That's why it occurs. So, as I said, we said, okay, how about if you make these measurements not statically, but fast, dynamically? So we have this setup where the soil is here, and then this is sand. And we have an oily liquid here. This is the non-wetting phase. Water is here. And then we put two pressure transducers here. These transducers, one of them is hydrophilic, the other hydrophobic. So one of them measures the pressure of the red phase, the other measures the pressure of the blue phase. So we can then measure, and they measure as the process occurs. So we can now plot Pn minus Pw as a function of time. And also saturation is measured. Now these are static curves that we get. We have this primary drainage. If you start saturation of 1, then you have main imbibition and main drainage. And now if you do it fast, the blue is those curves, you get totally different curves. These are called dynamic capillary pressure curves. So remember then, we were promised one curve because that was the premise of the theory, but we have now primary drainage curve, primary imbibition curve, main imbibition, main drainage. You have the scanning curves in drainage, a scanning curve in imbibition. You can have secondary scanning curve if you reverse process here in drainage and imbibition. And then you have the dynamic curves, drainage and imbibition. It's really a mess. And all of this is supposed to be given by that formula. It doesn't make sense. You need something more elaborate than that simple formula to be able to explain all of this. And so, as I said, yeah, the premise, well, it works, so we shouldn't worry about it, but it doesn't work in this term. There are also things happen that these equations can never model. For example, if you have dry soil and you put water on top of it. Now, you would think that this water, this is the yellow water appearing here, the water is being rained into this soil. You would think that that water will go in as a simple, nice front. It doesn't. It does this. Fingers will develop. Whereas it's fully homogeneous, as homogeneous it can be, homogeneous boundary condition, then you get these fingers. And what is more, along these fingers, the saturation, see, you would say saturation here is a small, oops. I need my pen here again. So saturation in this part is a small, and you would think, okay, it goes back to some wet part. So along this finger, if you measure the saturation, you would expect this. But you don't get that. You will get this, that there is an overshoot. The saturation is much larger at the tip of the finger. Now, such a non-monotonic behavior you will never get from the equations I showed you. They are diffusion type equations. And so we have done experiment where we said, okay, let's take one of these fingers and put the water there. Do I really get a non-monotonic saturation distribution in there? So this is where we took a glass tube, 50 centimeter, filled it up with sand, regionally homogeneous, at different initial conditions, initial saturation, and we rain water on top. And then when we measure saturation, this is a gamma system, that using gamma ray we measure saturation at different places. So at 20 centimeter, these are the curves. These are different flow rates. So just take one of these curves. The saturation is 0 in this particular place. And then the front comes, saturation goes up, and then goes back to some background value that is to come. It's always non-monotonic, unless if the flow rate is really small or the initial saturation is high. It only happens if you have a dry soil to start with. Now, how do you model this then? You cannot model it with the equations I showed you. And the pressure also is non-monotonic.
Are you sure that the sand grains will not move in your experiment?
Correct, yeah, definitely. This has been packed. They are being supported at the bottom with a permeable filter. Not with big, there's nothing, no reason for them to be moving.
What's the reason the channel
Yeah, but we can also see from the surface of the sand grains. They are totally as nicely packed as we can have them. Even if they are moving, I'm not sure you will have this non-monotonic behavior there, but any movement would be really infinitesimal.
So you've tried these experiments at different flow rates. Have you done it with different fluids with different relative densities or different surface tensions, that sort of thing?
We have done it with two liquids. This was air and water. We have done it with two liquids. We get exactly the same things. Non-monotonic behavior.
But in terms of the height of the jump and that sort of thing?
They would be different. Yeah, you will have different an effect there. Definitely, yes. So the fluid pressure and saturation are not the only state variables. There must be something that accounts for the fact that these menisci are there. There is interfacial energy playing a role. And pressure gradient and gravity are not the only driving forces. Imagine for single phase flow, okay, these are, so that means two phases. These are the only, but when you go to more fluid phases present, there are other effects, the capillarity effect that should appear in the equations. So we have gone, I'm not going to go through the procedure. We have followed a rational thermodynamics, a systematic procedure to say, okay, what should the equations look like? And what we find, of course, the mass balance for each phase, where this N is porosity, S is saturation, rho is mass density, this is Darcy flux, and this is the exchange of mass between the phases. If we assume rho to be a constant, now we get this, we have seen it before. This is the volume balance equation. But what we also get extra through averaging is that there is a similar equation for the masses that are accumulated potentially at the interfaces. And then it looks like this, where gamma is the mass per unit area of interface, and this A is called the specific interfacial area. This is area of alpha beta interface per unit volume of the porous medium, REV. So it's called the specific, and then there is a balance for this. If the mass density, mass per area is constant, then we get an area balance equation. So we have an extra equation. We also find that Darcy's flux is not related to pressure gradient, but related to the gradient of Gibbs free energy. This is a derived result. The only approximation is that we have assumed there is a linear relationship. And this Gibbs free energy, in case of only two phases, so what we call single phase flow through porous media, is a function of mass density and temperature. And there, then you can show that rho del G is equal to del P. So you get Darcy's law for single phase flow. But when you have more than one phase, then this Gibbs free energy is a function of density, but also area of interfaces, as well as saturation and temperature. And then if you put that in there, you get this as Darcy's law, where the pressure gradient and gravity are not the only driving forces. You have potentially other driving forces that contribute to energetic differences that cause the movement in the first place. I showed you those temperature changes. So these red terms are extra terms. There were these size or change of Gibbs free energy with the area or with saturation. We also find that interfaces also, their flux relates to the gradient of Gibbs free energy. So we have a sort of momentum balance for the interfaces. If we put all these together, these are the extended, truly extended equations. The red is the new part. So there is a balance for the interfacial areas, movement of interfaces. What we also find is that the pressure difference between the phases is not equal to capillary pressure. There is a dynamic term. And this now accounts for all those capillary pressure curves I showed you. I said it's a mess. Now we have a more complex formula. And the capillary pressure is not just a function of saturation, but also interfacial area. It's the distribution of phases. So the red is new. Now, I'm not saying, okay, so now, from now on, we should start using this. It could be that under certain conditions, some of these terms are negligible. That would be great. Then we neglect them. But you have to have them first before you can neglect them.
And that's the idea of a complex setup theory for a complex system and then make simplifications.
Do these area terms account for the polydispersivity of pore sizes? Or is that another factor?
It is related because, you know, as I mentioned earlier, the interfaces or the non-wetting phase doesn't move into every pore. It only can move if the pressure allows it to move in there. So if indeed you have a polydispersed pore size distribution, it will also affect that. But that will affect this. So here, instead of one curve, we have a surface. And so if you take this equation, what we really have is that this is the projection of a surface onto this plane of capillary pressure saturation. If you plot interfacial area, saturation, capillary pressure, then you get a three-dimensional surface. If you project it onto PCS plane, yeah, you get all these curves. That's what at least this is suggesting by this equation. And we have actually done measurements using our micromodels. Others have done that. You can get PCS curves and then lots of them, as I said earlier, the scanning curves. But then if you look at the PCSA surface and you put the data points, you get the same surface whether you put drainage data, imbibition data, scanning data, forms one single surface, which is nice because it really says that this way you can model hystresis, but not as curves, but as a surface. Yeah.
Can I just ask, are you inferring the plane of interfacial area, or are you measuring interfacial area saturation and capillary pressure?
Now, these are, when I say interfacial area, this is the, if you take an REV, representative elementary volume, and averaging volume, we have to count sum of all the interfaces within that REV. Is that your question?
Yeah. Yes, essentially.
Yeah.
So you, I mean, so experimentally, you've measured three measurements for each point on that plot.
Oh, correct, correct. Yeah, that's how we did it. And in this case, we did it with micromodels, and we used image analysis to determine the area of interfaces and saturation. There are also work done where they take this is a 2D porous medium we had, but there are also people who take a 3D porous medium soil sample and then uses CT scanning to determine distribution of phases, and from image analysis they again calculate saturation interfacial area. So these are all macro scale quantities, and indeed for every single point we have three things measured. And then we see that the two surfaces are really different by a small amount, and so you can really write a relationship between interfacial area, saturation, and capillary pressure. Now, that is related to this part. How about this part here? How does that help us to explain some of the things, the shortcomings I presented earlier? This is called dynamic capillarity equation. So if we neglect all the curves, interfacial area completely, only keep this extra term, how does that help us to, for example, model fingering and non-monotonic behavior? In fact, it does, because if one solves just this set of equations, then you will find that in a homogeneous system, if you introduce water on one side, then you get these fingers and the non-monotonic saturation distribution. This is numerical result. And we have been then trying to model our own experiment, as I mentioned, and we just model it with this set of equations. Yes.
What sets up the tau, actually, that you have, the time scale for this dynamical term?
The tau has to do with the following, that imagine, you remember the measurement of capillary pressure, saturation curves. It's an equilibrium process. You change the capillary pressure, and then you wait.
You look at the relaxation to...
Sorry?
You look at the relaxation to the new equilibrium, or?
And then indeed, if you are at equilibrium somewhere with a given saturation, given capillary pressure and pressure differences between phases, nothing is moving. Now all of a sudden, you change the pressure of one of the fluids. You have changed capillary pressure, but saturation hasn't changed yet. It needs time for saturation to develop to that new capillary pressure. And that time is characterized by this tau value. Correct. So it's, that's why they also, the more open, the more permeable the system is, the smaller tau value will be actually. So we get this. Another, and now if you go, I want to give an example where introduction of interfacial area also helps you to model a process. This is an experiment that we have also done where we say take a sandbox and put in this sandbox the same soil. So it's the same sand in here, but then make the saturation in one area smaller than the other area. And at time t equal to 0, remove a barrier that's between them. That's what we did. So saturation here is 1, here is 20%, and then at time 0 we had a very tiny, less than 100 micron thick barrier that we removed. Now then redistribution will take place. From wet part, water will go to the dry part. The reason it goes is that because the dry part is sucking the water. It likes to have it next to it. At the same time, the wet part doesn't want the water let go. So this part undergoes drainage, this part undergoes imbibition. If you use one PCS curve and model this, you will see that you get a full redistribution. After equilibrium, you will have the same saturation there. So this would be if you have no hysteretic effect. But we know that we have hystresis. You know that, remember these curves? The PCS curve looks like this. This is drainage, this is imbibition. I'm sorry, this is not writing well. So one part is doing drainage, the other part is doing imbibition. And once the capillary pressure is the same, then you will have no flow. But the capillary pressure is the same, that means one part will be a different saturation than the other part. And that's what you see here. At equilibrium, you will have this green part. Then we try to model, that's with the standard equations. You can get that. Then we also try to model using these equations, and in fact we find, so remember in here, in order to get this difference in the saturation between the two parts, you have to put two different curves for the drying part and the wetting part. But now we put one surface, a single surface for every part of the domain, and we still get that there is a jump in saturation survives. You get that the saturation in this part, the dry part, is lower than the wet part. So we can model hystresis by putting in interfacial area as an additional state variable. So I think I'll stop there. So the driving forces in Darcy's law should be not only pressure gradient and gravity, but in two-phase flow, that's three-phase system, you must include capillarity, which is an interfacial property. And then we will have other driving forces there. The difference between fluid pressures is only equal to capillary pressure under equilibrium conditions. Otherwise, we have to have that dynamic effect. And as I said, in addition to pressure at saturation, we need another state variable that relates to the fact that we have these menisci between phases. And the hystresis can be modeled by introducing this interface. But these interfaces are also very important when you have mass flux between phases. When you have a kinetic mass transfer between phases, occurs through interfaces. Or if you have kinetic heat transfer between phases, occurs through interfaces. So you need to have a knowledge of how much interface is there to model any kinetic mass or heat transfer among phases. Okay, I think I'll stop there. Thank you.
Questions?
Over here.
I have a question
Oh, okay.
here.
And then I gotta go to Mark. Okay.
What is the basis?
Victoria.
What is the
Yes.
Does it work? What is the basis for your extended Darcy equation? How did you derive it?
Yeah. So we started with the picture like the one I showed you with the interfaces you could see within the pores. If you start with that picture, and that is what we call microscopic
picture of the system. Then we see that there are 3 phases. But we also see that there are 3 interfaces. So the microscopic balance laws that we write for every point within each phase, but also for points on the interfaces. And the microscopic balance equation for interfaces are different than the one for the phases. Now when we average this using volume averaging, then you get average laws for each phase, but also for the 3 interfaces. And then we use the second law of thermodynamics, which makes use of the fact that entropy production must be non-negative in order to derive the equations I showed you. So that's how it comes in. If you remember the equation with the this equation, for example, we derived this, we obtained it, and I was trying to get rid of this term because all I had learned during my earlier studies what Pn minus Pw must be equal to Pc. No one has ever derived this. You cannot derive it by a volume averaging either. So I tried to get rid of this term. It wasn't possible. And I didn't know what it is. I said, okay, well, that's the way it is. That's the way it is. And it was only later a soil scientist told me, yeah, people have done fast drainage experiments and have measurements of these terms, and they find that they are not equal. And that's why I said, oh, so it must be this extra term. So we get derived equations that we didn't know we should have, actually. Because sometimes people do derivation, they know what they want to get, so they make assumptions to get it, and I don't think that's the right way either.
Then what is the definition of capillary pressure?
So the capillary pressure here is the one we measure under static conditions. If nothing moves, then these two are also indeed equal. But, okay, we measured those curves, they're great, we can use them, but now if something moves, then this is not equal to that, there would be an extra term involved.
A question back here, go ahead, Mark.
Can you hear me?
Yes, Mark.
So Majid, I really like this experiment with the water wicking and the temperature change at the wicking front. I think that's really cool. But I was just curious on the last experiment that you showed with the sort of, you know, essentially capillary with the imbibition. In this one. So when you did your extended theory, what kind of, you know, how did you, or what kind of parameters did you have to choose for all these other, for example, the creation of interface? I mean, that's sort of interesting how you model that, right?
So actually we modeled it with just forgetting these terms here. We had this, so the area balance, we had this, and then we even didn't include this part. So the main thing was to include interfacial area as an extra variable. And this surface, we obtained it by getting the hysteretic curves for that soil and then saying, okay, what should be the surface that gives you those hysteretic curves? So that's how we obtained this one here.
So was EWN0 or?
EWN.
This
one, no, it's not 0.
No.
No. So this is the production of interfaces. As you have seen, when you start with the system filled with the wetting phase, the interfaces come in, and you see there is in the beginning nothing, and then one interface, when it goes from one pore into 4 pores, breaks into 4 interfaces. That's a production of interfaces. That's the term there.
I guess, how do you model that?
And
that's the secret, right?
Yeah, that's a good point. For the micromodel that we had a full image of processes that occurred, we simply calculated that. Because from one time frame to another time frame, we could determine for a given REV how much interface came from the boundaries, that's this term here, but how much interface was created within that REV, and that's this term here. So that we could calculate
experimentally.
Sorry?
You calibrated it experimentally.
And for the micromodel, actually, we had it. But for the soil, we had to calibrate it. Correct. Correct. Yes.
Is this working?
No.
You put the button up. Yeah, it should work. It's working now, I hope.
Yeah, red light was on for a moment. It's temperamental.
I will repeat.
I
will repeat the question. I'll repeat the question.
Is EWN a simple function of those two, or is it a functional over past times?
Good question. And in fact, I am afraid it's a function. It's a function of past times as well. It's a function of the SDT.
You've answered me. Thank you.
Because, as I said, in fact, I have curves that we have measured for our micromodel. It's a linear function of the SDT. So that's maybe how the past comes into the equations, the history.
So there are systems where the anisotropy of surface energy definitely matters, such as ice crystals and maybe olivine crystals. Is it beyond imagining to do all this with orientation-dependent surface energies and a convolution over the orientations?
Get out. That's my answer. No.
Well, it's a fair question. Look, if you have a more complex system, you must expect to have more complex set of equations. I wouldn't know how would change this, and I'm not sure the procedure I have will allow itself to be used for this, but we can look into that actually. Yeah.
Can I just follow up? I mean, I hate to be the third person picking on EWN, but
No problem.
If you're
It's an important term.
if you're creating this interface, you have to be creating interfacial energy too, and so this must be dropped in from some energy source.
Correct.
Where is your?
Yeah, so depending on which process you're doing now. Let's say you're doing what we call spontaneous imbibition. It happens by itself. So there is a lot of energy released, I showed you that, from replacing the solid air surface, in this case with water solid. And that part of it goes into this creating the interface. But this interfacial tension between air water is much smaller than between air solid. If you're doing drainage, it will not happen by itself. You have to put in energy. And you have to inject something. Then it will happen. And that's how the source of the other energy is.
Equation, but all right. Okay. Any more questions?
Time for spontaneous imbibition.
Takes you to a lower energy state.
Okay, let's thank our speaker and
Thank you. Thank you.